So last video I talked about set notation, and I just want to make some comments on the empty set because that's what I finished talking about in the last video. I just wanted to make some clarificatory remarks. Okay, so I said in the last video that the empty set was like a zero with a line through it. And by that, I just meant that it looks like a zero with a line through it. It isn't actually meant to be a zero. Okay, it is the ancient Greek letter phi written like this. Okay, so that's the empty set. And I also said that a common mistake, okay, so this is the empty set. I said a common mistake was to write the empty set like this. Okay, and just while we're at it, this is also another way of writing the empty set, to just write two set brackets without writing any elements between the brackets. Okay, so this here is not the empty set. Okay, and the reason it's not the empty set is because it's just not empty. Okay, there's a set, and in between the set brackets is another set. So it's a set that contains a set. Okay, and whilst the notion of an empty set might be counterintuitive, okay, you can think of it like folders on your computer hard drive that you use to organize all of your files. Okay, there's nothing counterintuitive about making a new folder on your hard drive and not putting any files in it. Okay, it's a bit strange to do, but there's nothing counterintuitive about an empty folder existing. Okay, you can just make one. Right, so that's a bit like what the empty set is, and you can see that this here is like the scenario in which you had, like a folder, and you put inside it another folder. Okay. All right. Now the folder inside the outer folder is empty. That folder is the empty set, but the outer folder is not empty. It contains a folder. Okay, so that scenario is like this. Okay, so that scenario is like this, these two here. Okay, now I also talked about set operations last video, and some of the set operations I mentioned were union and intersection. So the union of two sets, the intersection of two sets. I also mentioned the subset relation, two sets being equal. So we can define new sets with these set operations, union and intersection. And I also talked about being able to define a set in terms of a common property shared between all of the elements in that set. And that's the kind of thing you do when you have a finite set and it's tedious to write out all of the elements of that set. So you just refer to the set by a common property shared between all of the elements. And it turns out, however strange it may seem at first glance, that we can do this as well with the empty set. Okay, so when you define a set in terms of a common property between the elements, that's a bit like saying the set is a club. Okay, so take an example. Let's say A equals the set of all x in the natural numbers, and if you don't know what the natural numbers are, we are going to talk about them in this video, such that x is even. Okay, and this is actually an infinite set because this set equals 2, 4, 6, 8, and so on. Just all of the positive even numbers. Okay, and you couldn't list them all. And defining them in terms of a common property would be, a more precise and complete way of defining that set. Okay, because you see here, you're just kind of grasping what the set must be by assuming what the pattern is. Okay, whereas here, there's nothing to assume. Everything is precise. So we can do a similar thing with the empty set. Okay, so first, let's just construct another set. And we'll call this set, use a different color. We'll call this set B. And B equals the set that contains 1 and 2. Okay, now let's define the empty set in terms of a common property shared between the elements of the empty set. And that seems counterintuitive because we know that the empty set doesn't have any elements. So how can there be any common properties between any of its elements? Well, consider this. Think of a set a bit like a club. Okay, and you can see that in this case, okay, A is a set, right? A is like a club, and to be a member of that club, to gain entrance, you need to satisfy a certain property. You need to satisfy some conditions. Okay, so to join the club of motor vehicle drivers, you need to satisfy the condition of having a license. Okay, to join a motorcycle club, you probably have to own a motorcycle. Okay, so there's some conditions for getting into sets when you define them in terms of a common property shared between the elements of the set. Okay, well, let's define the set of all x in some other set which we know exists because we constructed it, the set of all x in B. Okay, and B didn't have to be the set that I just constructed. It could have been any other set so long as we're happy to say that set exists. Okay, such that, okay, so you'll recall this symbol from the last video. And now we need to give it a common property, right? We need to give a condition for being in that set, right? But the thing is, we don't want any elements to make it into this club. We don't want this club to have any members because we are trying to define the empty set. Okay, so we can't just pick any old condition or property, because chances are for any property you pick, not any, but most properties, okay, the vast majority of properties you pick, there will be a bunch of elements that satisfy that property, and we don't want that because then we'll have people getting into our club, and we don't want anyone to be in our club. We want it to be a club that doesn't have any people in it. So the kind of property we have to use is a contradictory property, a property that just cannot be satisfied. Okay, and there are many contradictory properties we could choose, but this is a rather simple and nice one that will do the job, such that x is not equal to x. Okay, and take a second to convince yourself that nothing satisfies that property. Okay, I mean, if x, it's the set of all x in B such that some property is satisfied. Well, if x equaled 1, okay, because there's only 2 elements in B, well, x would be equal to itself because 1 is equal to 1, and if x equals 2, well, x would be equal to itself because 2 is equal to 2. And in fact, no matter what x equaled, and no matter what prior set that we pulled the x out of to make this new set, x would always be equal to itself because everything is identical to itself. You are identical to yourself. Okay, so nothing satisfies the property x not equal to x, so therefore nothing makes it into this club, and we have succeeded in defining the empty set. Okay, so in Australia, which is where I live, the legal drinking age is 18. Okay, so we could have also said the set of all bars in Australia that serve alcohol in which none of the patrons are breaking the law and in which there are people under the age of 18 drinking alcohol. Okay, no individual or no bar can satisfy both of those conditions, okay? Because if none of the patrons are breaking the law, then none of them are drinking alcohol whilst being under the age of 18. So we could have easily used a condition like that to define the empty set, okay? It just doesn't sound very mathematical, and it's a bit more convoluted. Okay, so we used a property like the one I just showed you. Okay, so moving on, let's get off set notation now and talk about different sets of numbers. Okay, so the real numbers. A real number can be represented by a decimal expansion, whether it's finite or infinite. Okay, so it just means the expansion can terminate somewhere or it can just string on, never ending. And the set of real numbers is denoted by this symbol here. The set of real numbers is denoted by this symbol here, okay, and it contains several important number systems itself. Okay, so obviously when we are writing by hand, we can't make our symbols appear like the typeset symbology that you see here. So in handwriting, the set of real numbers is denoted like this. Okay, so one of the number systems it contains is the natural numbers. Okay, and that's denoted by this symbol here, an N, and they are just the counting numbers 1, 2, 3, 4, and so on. And in handwriting, the symbol for the natural numbers looks like this, or sometimes people will write it like this. Okay, they are the same thing. Now I should probably comment now that there are two types of people in the world, right? There are people who treat 0 as a natural number, and there are people who don't include 0 in the set of natural numbers. Okay, and there really isn't a right or wrong when it comes to this. It just depends on what's more convenient for the kind of mathematics that you are going to be doing. Okay, so mathematical logicians tend to treat 0 as a natural number. Mathematicians that are working in theoretical computer science tend to treat 0 as a natural number. The motivations for that are many. For example, binary code in computer science, which is just a language of which the alphabet consists of 0 and 1, and they form words by just stringing together zeros and ones. If you treat 0 as a natural number, then you can say that the alphabet of binary code consists of natural numbers, specifically a subset of natural numbers, 0 and 1. Okay, and that's quite convenient. However, algebraists, so people who work in algebra, they tend to exclude 0 from the natural numbers. People who work in number theory tend to exclude 0 from the natural numbers. Okay, when you are doing a mathematics course, it's often good to check what the convention of your course is, whether or not 0 is going to be included as a natural number or not. Okay, it's most common to not include it in my experience. Maybe some people found the opposite in their experience. So even though I'm one of those heathens who includes 0 as a natural number because I really like mathematical logic, I've defined it this way in this video series because that's what I think you are more likely to see. Anyways, moving on. So the integers are denoted by this symbol here. It's an uppercase Z, and the reason it's a Z is because it stands for the word Zahlen. Okay, so Zahlen. Okay, I don't know if it's spelled like this or with the H there. I'm not too sure. Okay, but it's pronounced Zahlen, and that is the German word for integers. Okay, and in handwriting, it's often written like this. Okay, so they are just the positive natural numbers, the negative natural numbers, and 0. Okay, assuming that we've defined the natural numbers the way I have up here. If we included 0 to be a natural numbers, to be in the set of natural numbers, then the integers would just be like tacking on the negative whole numbers to the natural numbers. Okay, on the left-hand side of 0 on a number line. Anyways, moving on. Rational numbers are denoted by this symbol here. Rational numbers are denoted by this symbol here, and they are the real numbers that can be represented in the form a over b, so they can be written as a fraction where a and b are integers and b is not equal to 0. Okay, so this is very important. B cannot be equal to 0 because we can't divide by 0. Let's motivate that rule by a bit of intuition. Okay, so everyone knows that you can't divide by 0, but it's not necessarily clear why. Let's take 18 divided by 6. Okay, so we're going to divide 18 by 6, and I'm going to give you lots of 6, and you tell me when to stop when we hit 18. So I'm going to give you one lot of 6. Now I'm going to give you another lot of 6. Okay, and then I give you another lot of 6, and it's about now that you'd say stop. We've reached 18. Okay. But now let's consider 18 divided by 0. Okay, now you tell me when to stop. I'm going to give you 0 lots of 18. Okay, now I'll give you another 0 lots of 18. I'll give you 0 lots of 18 again, and it just isn't clear when to tell me to stop. Okay, it seems like I've got nothing. It seems like I never get anywhere. Okay, and this does not equal 0 as well, because okay, so we don't say that this equals 0 because it's just not clear what this means in the first place, so it doesn't make sense to say it's equal to something. Okay, it doesn't make sense to say that something which we don't understand is equal to something which we do understand, and we do understand the number 0. Okay, so that's straightforward. And moving on, so the rational numbers can be written in decimal form. So, and in decimal form, each rational number is either terminating or a repeating decimal. Okay, so for example, if we have 1/4, well, that's equal to 0.25, and you see this terminates. It doesn't just go on forever. Okay, but if you take, for instance, 1/3, well, that equals 0.3333, and that goes on forever. Okay, so it doesn't terminate, but you see how there's a repeating pattern. Okay, and note that the number, you don't need to have like the same number repeating again and again. There just needs to be a repeating pattern. Okay, so for example, this would also be a rational number, 0.125125, and repeating just like that. Okay, that would also be a rational number. Okay, so the way we write the symbol for the rational numbers when we are writing by hand is just by writing a Q and then putting a line through here like that. Okay. Moving on, the irrational numbers are denoted by this symbol here. Okay, and they are the real numbers that are not rational. So in decimal form, it's the opposite to the rational numbers. Each irrational number is a non-terminating, non-repeating decimal. Okay, so the decimal expansion doesn't stop, it goes on forever, and there's no repeating pattern. Okay, and it's not just that we can't figure out a pattern. Okay, we know there really isn't a repeating pattern. Okay, so it's not a matter of ignorance. So for example, pi, the number pi, is roughly equal to 3.14 and so on. So this number goes on forever, it doesn't terminate, and there's also no repeating pattern. Okay, and it might seem strange to say that we know this, even though, because you could ask, well, the pattern goes on forever, so how do you know that there isn't a repeating pattern? Because you can't check the whole decimal expansion, it's too big. There are methods for proving this. It's beyond the scope of this course, but it can be proved that something is irrational. I will show how to prove this kind of thing in a video series on discrete mathematics, and the topic within that will be number theory. Anyways, the way we write the symbol in handwriting for irrational numbers is just like the rational numbers. We draw a Q, but we draw this swiggle on top. I'll draw it a little bit better, and that's called tilde. Okay, so an easy way to remember this is that in formal logic, a tilde like this means not. Okay, so drawing a tilde and then underneath that, drawing the symbol for the rational numbers is like saying not rational. In other words, irrational. Okay, so moving on. So this diagram just shows how these sets of numbers are related. Okay, so you can see that the natural numbers is a subset or is inside the integers, and that's inside the rational numbers, which is inside the real numbers, and the irrational numbers are kind of a funny one because they don't exist inside any of these on the left hand side of that vertical bar. They kind of just sit out here on their own, but they do sit inside the real numbers. Okay, so moving on, the set of real numbers can be represented by a number line. And even though on this number line we have only written integers, okay, it's assumed that all of the real numbers are there filling in the gaps, okay? So it's assumed that 1/2 is here, okay? And, you know, pi is here somewhere, right? So there's pi, okay? And e is like, you know, somewhere around here if you're familiar with Euler's number. Okay, so all of the real numbers are sitting here. Okay, and perhaps you've heard of complex numbers and imaginary numbers. Okay, so I will talk about them pretty soon in this video series, but those kind of numbers don't exist anywhere on this line. So that's interesting. More to come on that front. So anyways, you're probably all familiar with these symbols. You know, so the first one is less than or equal to. The second one reads strictly less than, but we often just say less than. We have greater than or equal to, and strictly greater than, but we often just say greater than. You will recall this one from a previous video, this one here. So that's the subset relation, or is a subset of, and this one here, okay, Greek letter epsilon reads is an element of or belongs to, but we often really just say is in. Okay, so you know, like 2 is in the set of natural numbers. Okay, so note from this diagram above here that shows how all of these systems of numbers are related, or these sets of numbers are related. You will see that the natural numbers, okay, is a subset of the integers, which is a subset of the rational numbers, and then the rational numbers are a subset of the real numbers, okay? And here, the irrational numbers are just sitting out on their own, okay? So another way to think of this, where you can see up here in the diagram, the poor old irrational numbers are just sitting on their own, is like this. Okay, if you take the intersection of any of these sets here with the irrational numbers, they will share no elements in common. So for example, let's take the natural numbers. They are my favorite set of numbers. Okay, they might seem like really simple and boring ones, but for various reasons they are my favorite. So if you take the natural numbers, take the intersection of the natural numbers with the irrational numbers, they share no elements in common because all of the elements in the natural numbers are just positive whole numbers, and all of the numbers in the irrational numbers are just numbers that are non-terminating extensions with no repeating pattern. Okay, so number just by whole, it doesn't have a terminating. uh, would be, okay, which is anyways. So here is a cheesy story to help you remember how all of these sets are related, in terms of the subset relation. Okay. So I found these pictures and I tried to draw them. Okay, and one is of a cave woman and one is of a cave. Okay, very terrible drawing, I know, but let's name them. Okay, so let's call her Sarah and let's call him Bob. Okay, so suppose back in the days of cave people, uh, Bob and Sarah fish. That's how they get their food. They go fishing. Okay, and Bob likes to count his fish. So on some given day, Bob will count his fish, and this is the set of all the fish he has. He has one fish. On some other given day, he might have more luck fishing. Actually, don't worry about sets. Let's just, like he'll count his fish. Okay, so maybe on one day he has 7 fish. He eats a few. Fishing isn't going so well. He's down to 4 fish. Okay, and if you look at Bob's teeth, he's got some big chompers. It probably can get through a lot of fish with teeth like that. Okay, he's looking a little crazy with those eyes. Maybe he has some mercury poisoning or something like that. But he eats too much fish and he gets down to 0 fish. Okay, now previously when Bob was counting his fish, he could he could refer to however many fish he had until he had no fish left. Okay, so before he was able to just make do with natural numbers, but now he has no fish left, so he needs to introduce a new concept to capture how many fish he has left, namely none. Okay, and he'll introduce 0. So now we've gotten out of the natural numbers. Okay, but Bob still needs to eat. Okay, and Sarah, let's say Sarah has 10 fish because she's responsible. Okay, so Sarah has 10 fish and she's kind enough to lend some to Bob. Okay, well, how many fish does Bob have? One way of thinking about it is that suppose she gives him 3 fish. Okay, so 10 minus 3. One way of thinking about it is to say that Bob has 3 fish. Okay, but this doesn't really capture the same scenario as when Bob just has 3 fish because he caught the fish when he was fishing. So it seems like we need to add something else to capture this extra fact about Bob's fish, and by that I mean we have to introduce new kinds of numbers like this, negative numbers. Okay, so we need to be able to describe the fact that Bob has no fish. Bob has negative 3 fish, so he owes some fish to Sarah. And before we were able to capture how many fish Bob had just by using the natural numbers. Okay, but suppose Bob is just so greedy with his fish and keeps borrowing from Sarah, and Sarah's just too nice that she can't let Bob starve, okay, because it's going to be hunting season soon, and Sarah thinks Bob is pretty good at hunting, and when the fish aren't doing so well, she's going to rely on Bob to hunt saber-toothed tigers or whatever, or woolly mammoths. Sarah starts lending Bob fish, but she becomes a little bit more stingy and she starts cutting the fish up. Okay, so we still need to keep track of how much fish Bob owes to Sarah, but we are not going to be able to capture this fact in terms of natural numbers or negative numbers. So we need to introduce new kinds of numbers. Maybe Sarah gives half a fish to Bob. Okay, so now we have rational numbers, okay, which are either positive or negative. Okay, so that's how we get from the naturals to 0 to the integers and to the rational numbers. The story doesn't really capture how we would arrive at the irrationals. Okay, but let's suppose we also arrived at the irrationals somehow. Okay, well then, in one sense, to get to the reals, we can just say put them all in a set and they would be the real numbers. Okay, but that's not really how we end up defining the real numbers. But it's a convenient way to think of it. It won't lead you astray. Anyways, I think that's everything I wanted to cover. So if you enjoyed this video, please give it a like, subscribe, and perhaps share it with your friends. In the next video, I will be covering interval notation. Bye for now.